Hello, so in this video we will talk about a concept called partial ordering, which is defined as a relation R, which is an antisymmetric relation, reflexive relation, and transitive relation. So antisymmetry is what? That if A, B is there, then B and A cannot be there. And thinking that A and B are different elements. In technical terms, we can say that if AB belongs to R and BA belongs to R, then A is equal to B. Okay, but this is a better way to remember, for me at least, that if AB is there, then BA cannot be there. Okay, so partial ordering set or poset is actually a set along with the relation written together. So typically we write set S and then a relation. Typically this symbol is used. Okay, this is because this is the closest symbol to the less than sign, and less than operator is the most common operator for anti-symmetry. Okay, and you can, a reader can check that it is reflexive and transitive as well. Okay, the most common representation of a partial ordering is through a Hasse diagram. So what do we do is we draw the diagram of the partial ordering R or S normally, but we remove the loops. Remember, loops are there because of the reflexive property, and then we remove all the edges that are present due to transitivity. So for example, if we have A to B and B to C, then through transitivity we should have this arrow as well, so we remove this. Okay, because this is obvious that since it is transitive, this edge is present. Okay, and then 3 is that we remove all the arrows, so there is no direction there. We assume that Hasse diagram is drawn from bottom to top. Okay, so if there is an ordered pair A B, so it is drawn like this. This is my A and this is my B, so it's obvious that it is going from bottom to up. Okay, then we talk about comparable elements. So if the associated relation can be formed between two elements, they are said to be comparable, and if every pair in a poset is comparable, that partial ordering is known as total ordering. So what does it mean? For example, we have a divide operation and the set is 1, 2, 3 and 4. Okay, so this is my divide. So now 2 divides 4, 1 divides 3, 1 divides 2, 1 divides 4, but 2 does not divide 3. So 2 and 3 are not comparable. Okay, so this is what it means. So if in a poset, if the corresponding set, all elements of the corresponding set are comparable, that poset is known as total ordering. Okay, then there are some definitions about minimal, maximal, least, greatest, upper bound. And so minimal element is an element A in S such that element B such that there is no element which is greater than A. Okay, in poset terms. And similarly, maximal is the mirror image of that, and least element is an element which is less than all the other elements of the set. So this may or may not exist, so we put a question mark here. Sometimes it exists, sometimes it does not. Similarly, greater than is an element for which all the other elements are less than that. Okay, so the word less than does not mean less than in terms of numbers. It means less than in terms of this operation here or relation here. So if there is a subset A of S, then we can find the upper bound of that subset if all the elements are subsets of that upper bound. So technically speaking, an element U in S is an upper bound of A such that for all elements A in capital A is less than U. Okay, and A is obviously subset of S. Similarly, least upper bound is chosen through all the upper bounds and seen, and we see that what element in this set upper bounds is a subset of all the other elements. So similarly, lower bound and greatest lower bound is defined. Lower bound is for a set A, all the elements which are the subset of or which are less than all the elements of A. And greatest lower bound is among those we found here, we choose the one for which all the other elements are subset. Okay, so this will be more clear when we talk about an example here. So now we have this set 1 2 4 1 2 1 4 2 4 3 4 1 3 4 2 3 4, and the operation here is the subset operation. So let's now draw the Hasse diagram of this poset. So we have 1 here, 2 here, and 4 here. So I will write 1 2 and 4. Then we have 1 2, so I will write 1 2 here. Okay, so this is my 1 and 2. Then we have 1 4, so 1 4, let me draw it here. So this is my 1 and 4. Now we have 2 4, so 2 4 is somewhere here. So 2 and 4. Then we have 3 4, so 3 4 is here. 3 and 4. Then we have 1 3 4. Okay, so 1 3 4 is obviously a superset of 3 4, but it's also a superset of 1, correct? And 1 goes to 1 3 4 through 1 4, so we only have to draw it here. Then we have 2 3 4, so 2 3 4 is obviously a superset of 2 4, so we'll write 2 3 4, but it's also a superset of 3 4, correct? So it is also a superset of 2 4 and then 2 3 4. Okay, and then 1 3 4 is from 1 4 and then 1 and 4. Okay, and it's also a superset of 3 4, 3 4 and 2 4. Okay, so this is our Hasse diagram. Okay, so what is the minimal element? What are the vertices here for which there is no subset? So 1 2 and 4. So minimal elements are 1 2, the set 1, the set containing 1, the set containing 2, and the set containing 4. Okay, so for maximal elements, we see how many elements are there for which there are no supersets. So this element, and this element. So we have 1 2 2 3 4 and 1 3 4. Least element. Is there an element for which everyone is greater than that? No. Similarly, is there a single element for which everyone is less than that? No. So upper bound of 2 and 4. So 2 and 4, one upper bound is obviously 2 and 4, and the other upper bound is where 2 and 4 connects to the next one, which is 2 3 4. Among them, the least is 2 4. Least means which is the closest to 2 and 4 in the Hasse diagram. Lower bound of set 1 3 4 2 3 4. So 1 3 4 and 2 3 4. One lower bound is obviously 3 4, and then 3 4 is connected to 4 as well. So we have 3 4, this is 3 4, and then just 4. The greatest of these is 3 4, which means that which is closest to the set under consideration, which is 1 3 4 and 2 3 4. Okay, so this is the greatest lower bound, and this is the low, these are the lower bounds. Okay, so this is actually a set of lower bounds if you want to say it. Okay, okay, so this is it about the partial ordering and the Hasse diagram, and how we can translate these definitions of minimal element, maximal elements, and so on into observation of a Hasse diagram. Uh, Hope you liked the video, and thanks for watching.